Failure analysis of buried steel pipe under common geological disasters, investigating structural risks from natural earth events. Introduction to buried steel pipes and geological risks. Buried steel pipelines are critical infrastructure for transporting water, oil, and gas across regions. Their reliability is essential for industrial operations and public safety. However, these pipelines are often exposed to geological hazards such as fault movements, landslides, ground settlement, and rockfall impacts. These hazards can lead to severe structural failures, leakage, and environmental disasters. Understanding the interaction between geological forces and pipeline integrity is crucial for engineers and decision-makers. This section introduces the importance of failure analysis, highlighting how geological disasters impose stress, strain, and deformation on steel pipes. It also explains why proactive design and monitoring strategies are necessary to mitigate risks. The introduction sets the stage for detailed discussions on specific hazards and their impact on buried steel pipelines, emphasizing the need for advanced engineering solutions and compliance with standards like ASME and API. Impact of fault movement on buried pipelines. Fault movement occurs when tectonic plates shift along fault lines, causing displacement of soil and rock layers. For buried steel pipes, this results in axial tension, bending, and shear forces that can exceed material limits. The magnitude of damage depends on fault displacement, pipe diameter, burial depth, and soil properties. Common failure modes include buckling, cracking, and joint separation. Stress analysis charts often reveal concentrated stress zones near bends and welds. Engineers use finite element modeling to predict deformation patterns and identify critical points. Real-world case studies show that pipelines crossing active fault zones require flexible joints and strain-absorbing materials. Mitigation strategies include route optimization, installation of expansion loops, and continuous monitoring using strain gauges and geotechnical sensors. Understanding fault mechanics is essential for designing resilient pipeline systems in seismically active regions. Landslide-induced pipeline failures. Landslides involve the downward movement of soil, rock, and debris under gravity, often triggered by heavy rainfall, earthquakes, or human activities. When a buried steel pipeline lies within a landslide-prone area, it experiences lateral forces and uneven soil pressure, leading to bending and ovalization of the pipe. Severe landslides can cause complete rupture or displacement of pipeline segments. Stress analysis indicates that landslide forces create complex loading conditions, combining axial tension and bending moments. Engineers mitigate these risks by conducting geotechnical surveys, installing retaining structures, and using flexible pipeline designs. Real-world examples include pipeline failures in mountainous regions where landslides occur frequently during monsoon seasons. Preventive measures such as slope stabilization, drainage control, and early warning systems are critical for reducing landslide-related pipeline failures. Effects of ground settlement on pipeline integrity. Ground settlement refers to the gradual sinking or subsidence of soil layers, often caused by groundwater extraction, mining, or natural soil consolidation. For buried steel pipelines, differential settlement creates uneven support, resulting in bending stresses and localized strain concentrations. Over time, this can lead to fatigue cracks, joint misalignment, and leakage. Stress analysis charts show that settlement-induced deformation is most severe at transition zones between rigid and soft soils. Engineers address these challenges by designing pipelines with sufficient flexibility, using settlement-tolerant joints, and implementing soil improvement techniques. Monitoring systems such as inclinometers and settlement markers help detect early signs of subsidence. Case studies reveal that pipelines in urban areas with high groundwater extraction rates are particularly vulnerable to settlement-related failures, emphasizing the need for integrated geotechnical and structural design approaches. Dynamic loading from rockfall events. Rockfall events occur when large rocks or boulders detach from steep slopes and impact the ground surface. For buried pipelines located near mountainous terrain, rockfall can cause localized surface deformation that transfers dynamic loads to the pipe. Although burial depth provides some protection, high-energy impacts can still induce stress waves and soil displacement, leading to dents, cracks, or coating damage. Engineers use impact analysis models to estimate energy transfer and potential failure modes. Protective measures include installing rockfall barriers, increasing burial depth, and reinforcing pipeline coatings. Real-world incidents in alpine regions demonstrate that rockfall impacts, though less frequent than landslides, can cause catastrophic failures if not properly mitigated. Advanced monitoring systems using acoustic sensors and geotechnical instruments help detect rockfall activity and prevent pipeline damage. Common failure mechanisms and analytical techniques. Buried steel pipelines under geological hazards exhibit several failure modes, including buckling, fracture, fatigue cracking, and joint separation. Stress analysis techniques such as finite element modeling and strain energy calculations are used to predict these failures. Engineers consider factors like soil pipe interaction, material properties, and dynamic loading conditions. Charts and diagrams illustrate stress distribution under fault displacement, landslide forces, and settlement-induced bending. Failure analysis also involves fracture mechanics to assess crack propagation and fatigue life estimation. Standards such as ASME 31.8 and API guidelines provide design criteria for pipelines in geologically active areas. Understanding these analytical methods is essential for developing robust pipeline systems and implementing effective maintenance strategies. Real-world incidents and lessons learned. Several documented cases highlight the vulnerability of buried steel pipelines to geological hazards. For example, pipelines crossing fault zones in California have experienced ruptures during earthquakes, leading to significant environmental and economic losses. In mountainous regions of Asia, landslides triggered by monsoon rains have caused pipeline displacement and leakage. Similarly, urban pipelines in areas with high groundwater extraction have suffered from settlement-induced failures. Rockfall incidents in alpine regions have damaged pipeline coatings and induced localized deformation. These case studies emphasize the importance of comprehensive geotechnical surveys, advanced design techniques, and continuous monitoring. Lessons learned include the need for flexible joints, protective barriers, and early warning systems to minimize risk and ensure pipeline integrity. Design and operational measures for risk reduction, mitigation strategies and monitoring. Mitigation strategies for buried steel pipelines under geological hazards include route optimization to avoid high-risk zones, use of flexible joints, and installation of protective structures such as retaining walls and rockfall barriers. Soil stabilization techniques and drainage control help reduce landslide and settlement risks. Advanced monitoring systems using strain gauges, inclinometers, and acoustic sensors provide real-time data on pipeline and soil conditions. Engineers also implement predictive models to forecast hazard impacts and schedule preventive maintenance. Compliance with standards like ASME and API ensures that design and operational practices meet safety requirements. These measures collectively enhance pipeline resilience and minimize the likelihood of catastrophic failures. Summary of key findings and future directions. Failure analysis of buried steel pipelines under geological hazards reveals that fault movement, landslides, ground settlement, and rockfall impacts pose significant risks to pipeline integrity. Stress analysis and case studies demonstrate the complexity of soil pipe interactions and the need for advanced engineering solutions. Mitigation strategies such as flexible design, protective structures, and continuous monitoring are essential for risk reduction. Future directions include integrating real-time geotechnical data with predictive analytics to enhance hazard forecasting and pipeline safety. Adhering to international standards and investing in research will ensure that pipeline systems remain reliable and resilient in the face of geological challenges.